You can all hear me okay, right? Yeah, okay. Had a few technical issues. Right, okay, so how many of you in this room are currently using containers? Put your hands up. And leave your hand up if you are totally confident that you really know what a container is. Yeah. Yeah. So I've been working with containers for a few years now, and I know there was a period of time where I kind of heard things like lightweight virtual VM that didn't leave me with a very sort of satisfying feeling that I really understood what was going on. And then I saw a presentation by a chap called Julian Friedman from IBM, and he did something kind of similar to what I'm going to do today, and it really helped me understand what we're talking about when we're talking about a container. So hopefully that knowledge, you're going to leave here with a much greater knowledge and a much greater understanding of what we really mean when we talk about containers. Okay, so I'm going to be building a container this afternoon, and I'm going to write it in a few lines of Go. Have we got any Go programmers in the room? Few hands going up. You're going to be my peer reviewers. You're going to let me know when I go wrong. Hopefully for the rest of you, it doesn't really matter what the language is. And we're going to build a container out of 3 concepts in Linux: namespaces, changing the root, and control groups. So I'm going to talk about what those different things are as well as we go along. But before we start building our own, let's have a look at what happens when we run a container under Docker in the kind of normal way. Is that big enough at the back? Can you see? Wave your hands if it's not big enough. I'm going to take it that is. Okay. So we can do something like Docker run, and I want it to be interactive, and I'm going to remove it when it's done. And maybe I run based on the image Ubuntu, and I run a shell. So I can start with a container image, and I can run an arbitrary command sort of inside a container where that container is based on the image, in this case Ubuntu. And we've got a host name inside the container this is actually the identity of the container. So it's some kind of random identity that's been allocated. If I look at the processes running inside the container, I only see the processes inside the container, and they're numbered starting from 1. Whereas if I'm on the host, this is the same machine, but from the host perspective, I've got much higher process numbers going on. Okay. So I'm going to try and recreate something a bit like this Docker run. Let me quit out of this container. And the first thing I'm going to do is I'm going to talk about namespaces. So a namespace is where we limit what a process can see. So we just saw a container running, and it could only see a few of the processes on the host. And that's because it's got a namespace for process IDs. It could only see its own host name, and that's because of namespacing. And we set up these namespaces using syscalls. There are about half a dozen of them, depending on your particular version of the Linux kernel. And this is a big part of what makes a container into a container. It's restricting the view that a process has of the things that are going on the host machine. So I'm going to start with namespaces. But before I do that, let's remember we're trying to do Docker run, and I would normally do an image name, and then some command, and some parameters. In my Go program, I'm going to save this as main.go, and then I can do go run main.go, and that compiles and runs my executable. So that's kind of the equivalent of Docker. I'm going to have a command called run. It's going to become apparent why I need that. I'm not going to pass in an image, because I'm just going to, well, you'll see, I'm going to sort of give it an image later. And then I want my containerized process to run some arbitrary command, and there might be some parameters. So I'm going to have a main function, and the first thing I'm going to do is look at the command, so where I've got run as argument 1, I want to check that I've got run, and if I am, that's very happy, and I can run a function called happy that we'll write in a moment. And if we get anything else there for now, we are going to collapse in a big heap and be sad, because we don't like it. Okay, so now I need a run function. And for the moment, all I'm going to do is print out what it is that we're supposed to be running. So we've been given the command and parameters, and they are in the arguments 2 and onwards. So let's just check that we can run this. Sorry, go run main.go, and I need run as my command, and I might say, let's say hello Amsterdam. So all it's done at the moment is it's logging out the fact that I want it to say hello Amsterdam, but it's not even doing that yet. So I need to write a bit of code to actually run my command. And in Go, we do that with a command, an exec package. So I set up a structure for my command that I want to run. And I don't actually run it until I hit this run method. And what I want it to run is whatever the command is that was passed in argument 2, and maybe there are some other parameters as well. So 3 and on, maybe. I also have to wire up stood in, stood out, and stdr. So if I don't do this, we can't see anything going on, so that would be really dull. And I get to do multi-cursors, which is very exciting. Stood out and stdr. Okay, so now I should have the ability to run an arbitrary command. Let's check that out. I can pass in, I want you to echo hello Amsterdam, and it does echoing hello Amsterdam. And I could do something like run a shell. It's told us it's running a shell. You can't really tell because, well, what's going on? There's some processes here. This is our bash shell that I just started. So now I want to kind of containerize this command as I start it. And we're going to do that by creating some namespaces. And I can do that by specifying here in this command structure that I want namespaces, which I do with sysproc attributes. Attribute structure. And I'm passing in, it's called clone flags because cloning is what creates the new process that we're going to run our arbitrary command in. And as I do that, I want to create a new, we're going to start with the flag for Unix time-sharing system, which sounds incredibly fancy and powerful and like it's going to be really significant. But actually, all there is in the Unix time-sharing system namespace is the host name. But this is going to let us have our own host name inside the container, so it can see its own, it can't see what's happening on the host. Let's give that a try. So I'm going to run my shell again, and if I do host name, it's inherited the host name from my, my host machine. We'll just check they're the same. But I can change it here. Let's check that that's stuck. Yeah, so I've changed it inside my container without affecting what's happening on the host machine. So I've started to containerize my process. So this is a start, but it would be really nice if I could actually use this host name, if I could set the host name up before I spawn my shell so that I could see it in the prompt, because at the moment it's really hard to tell from the prompt whether I'm in my container or not. And you might start by looking up the Golang sort of method for setting the host name, and you'd find set host name, and we have to send it in as a list of bytes. So we might think we could do something like that, but we have a problem. If I call that function here after I've completed this run method, that doesn't complete until after I've exited the command that I want to run. So I can't do it after. And I can't really do it before, anywhere up here, because I haven't actually, although I specify that I want my namespace here, it's not until inside this run method that we actually clone this new process and actually get the new namespace. So I can't do it before, and I can't do it after. So what I'm going to do is I'm going to have this process clone a new process with the new namespace, and then I'm going to create another process in which I can have, in which I'm going to run my command. So I'm going to duplicate this, have one version called run and one version called child. So the first one is going to create the namespace. But rather than say, I want you to run the arbitrary command, I want this to run this program again, run itself. And we can do that by running proc self exe as the command that we want to run. We'll have a look at that in a moment. Oops, where's it gone? Right. And I want it to call itself, but instead of having run as that first command, I'm going to pass in child. Now, so when I come in here, I'm going to, if I see child as that command, I'm going to call this other version of the function down here. I have to do a bit of Go sort of syntacticness. I have to make this into a list of strings. And then I've got arguments 2 and onward. I think this is going to be about right. Okay. So I'm going to call run. Run is going to re-invoke this process, but inside its new namespace. The second time in, it's going to be calling child. And we don't need to create a namespace this time. But we do want to set the host name, because this time around it should already be in the new namespace. So let's give that a whirl. So straight away we can see a couple of things. We see the log happening twice because we've called it once inside run and once inside child. But more interestingly, the bash prompt has picked up that host name. So that's done what I wanted it to do. This is pretty good. And now we can more easily tell whether we're in the container or not, which is pretty beneficial. OK, so what if I now want to have PS return me just the processes inside my container? So at the moment, I haven't namespaced process IDs, and I'm still seeing the same kind of high-numbered processes that I can see. If I look at all of them, we'd find all of those processes up here. So like 7621, for example, there is my bash, corresponds to that. OK, so I want to see, inside my container, I want to see these starting from 1. Let's quit out of that. And there's another one of these namespace flags called new PID for process ID. And I'm also going to print out the process ID that we're running as, so get process ID. We'll do that inside run, and we'll also do that inside the child. Okay. That looks pretty promising, right? The first time we were running as some high-numbered process, when we were inside child, which should be inside this new process ID namespace, we've got the ID 1. That's exactly what we wanted. So, hands up if you think I can do PS and it's going to work. Yeah, oh, a few hands, okay. I am going to disappoint you. It's still finding those high-numbered process IDs. And the reason for that is because PS doesn't kind of magically get the process information directly. It gets it from the /proc directory. You remember a minute ago we looked at proc self exe? So /proc has information about all of the running processes. We can see them. There's a directory for each of the numbered processes. I'm just going to go back to the host for a minute. If I do something like ls-l for, let's look at proc self exe, and you can see that that is a link to, well, I was running ls, so it makes sense that if I do it again, well, you know, that's always what it's going to be. But if I go to proc self, we can see every time I get a new process ID, and proc self changes as we start a new process. And there's all sorts of interesting information inside /proc for each of the processes. We'll see a little bit more of that in a moment. PS is looking at this /proc directory. So inside my container, I need my own version of proc. At the moment, it's seeing the same, you know, from inside the container, it's seeing the same /proc. And this is where chroot comes in. I'm going to change the root of what the container can see. So at the moment, if we look at the root directory, I have marked it with this root for host file. I also happen to have a copy of an Ubuntu file system, Ubuntu FS, and this has got root for container in it. So I'm going to change the root for the container so that it sees this as its root directory. Let's quit out of this. So in here we can do chroot, and I want that vagrant Ubuntu FS directory to be my root. I'm also going to change the directory to root, because if I don't do this, it's actually undefined where you end up after you've done a chroot. Okay. So I run my container again, and now if I look in the root directory, root for container is it's in my root directory. I can't see anything higher up than root. That is my root. Inside my container, I've limited its view of the file system. But I could do something interesting like, so if I do sleep for a little while inside the container, from the host, we can find that sleep process, 7840, and if we look again in /proc for 7840, this is all the information about that sleep process. And there's a root directory. Let's have a look at what that tells us. And that shows us that for that process, the root is actually the file system that we just mounted. Now that's pretty much the equivalent of a container image. When you specify the image, it takes a copy of the file system that's packed up in that image, unpacks it into somewhere on your host machine, and chroots the container to see that new file system. So we've kind of done the equivalent. Okay, so back to the proc directory and back to PS, because if you remember, we're trying to get PS to show us just the processes that are running inside the container. And I did that to root so that I would have a proc directory inside the container. And there's nothing in it at the moment. And if I do PS, it's going to tell us what it is we need to do. So it turns out that proc is it's a pseudo file system. It's a mechanism for the kernel and user space to share information. And at the moment, /proc inside my container in the rooted file system has nothing in it. And I need to mount that directory as a proc pseudo file system so that the kernel knows I'm going to populate that with all the information about these running processes. So, in here, I can mount that. Very important that I get these parameters in the right order, as you can see. All right, and I'm going to tidy up after myself by unmounting them when we finish, unmounting it when we finished using it. Okay. So I need to run that again. And this time, what do you reckon? Will it work? Hands up if you think it'll work. Mixed confidence here. It works. It works. Look, there we go. Process ID number 1. Thank you. Right. One of the things we did there was we mounted proc, and we can see that mount inside the container. That's kind of what we would expect. There are quite a lot of things mounted on my host, so I'm just going to grep for things that relate to proc. From my host, I can see this one at the bottom, which is the same one that we've got mounted inside the container. We can tell that because it's inside that file system that I mounted. Now, there is a namespace for mounts. So, it is called new NS for namespace. Apparently, this was the first of the namespaces to be invented and added to the kernel. And I guess at the time, they didn't really think there would ever be a need for any other namespaces, so they called it namespace, but it's really for mounts. I also have to do something else here. Now, by default, under systemd, mounts get kind of this recursively shared property. And at the moment, my root directory on my host recursively shares between all namespaces any mounts. And I have to deliberately turn that off with an unshare. I'm going to say unshare flags for the new namespace. And by doing that, I can say, I've got this new mount space in my container, and I don't want you to share it with the host, because by default, it would have shared it back with the host. So, if I do this again, we can run our mount inside the container. We can still see proc. But on the host, I no longer see that proc. And that's how we can end up with, or we can avoid having like hundreds of containers cluttering up our mount command with all sorts of information about mounts inside the containers that we don't really care about from the host. I could find out about them by looking in the proc directory though, so I can do the same thing again with sleep and find that process from the host's perspective. And if I look at, I think I need to cat 8029 this time, and I think it's mounts, maybe? Yeah. So I can still see the mounts that this process is aware of from the host perspective, but they don't go cluttering up my mount command. Okay, so we have looked at the namespaces for the Unix time-sharing system, which is the hostname, for process IDs, and for mounts. And you can imagine how isolating things like your network interfaces so that your container only sees a specific set of network interfaces and user IDs and inter-process communications all work in the same sort of way. Okay, we also saw how chroot works and how that limits the container so it can only see a subset of the file system that the host can see. And there's one last sort of property of containers, and that's control groups. And if namespaces restricted what we can see from inside the container, a control group limits the resources that we can use inside it. And we do this, it's configured using another one of these pseudo file system interfaces. So it's another set of what look like directories and files, but we can manipulate them to set properties that we want the kernel to understand. And the kernel will write information into the file system so that we can read it back out again. And we could be talking about things like how much memory the container is allowed to use, how much CPU, how much I/O bandwidth it's allowed, and also how many processors are allowed, which we're going to use as an example soon. Wrong direction. Right. Before we do that, let's have a look at how that file system looks. And it's typically in sysfsc group. I'm going to change into that directory. And we have a directory for each of the different types of control group that we can set up. And let's use memory as an example. So we'll go in here. And there's actually a large number of parameters that you can set related to memory. And I could look at, let's say, memory, what is it, limit in bytes. That gives us a very, very, very large number, which is basically saying, by default, processes can use all the memory in the system. Also, we've got this Docker directory, which Docker presumably set up. We'll have a look in there. And at the moment, it's just got another set of all the same parameters. Some of these are also sort of statistics being reported back into user space. And let's see what happens when we run a container. So if I do exactly the same as I did before with Ubuntu, and I run a shell, and we've got a container that starts with the ID 070C. And now we've also got a directory inside the control group structure starting with 070C. So Docker has created a control group, basically, for this container. But we didn't ask it for any particular restrictions. And if we were to look at what's inside that memory limit in bytes, it's not restricted. It's still a massive, I don't even want to count the digits for that. Let's see what happens when we do constrain the memory. So I can say memory is, let's say, 10 megabytes. And this time it's F497 is the identity. In here. We've got a control group F497. And if I look in the limit this time, that's basically 10 meg. So Docker wrote that number into that file, and that's how it tells the kernel to limit that particular container to that amount of memory. So we're going to do the same kind of thing. And we're going to do it for the number of processes. Actually, let's just have a quick look. So inside PIDs, we can see things like oh, it hasn't got the maximum number. Okay. Well, I know how we can look at it. We can look at it inside Docker. And there should be a PIDs max. Yeah, so by default, when you create a Docker container, there is no limit to the number of processes that can be spawned inside that process. But I'm going to create a control group that does limit the number of processes. And I've got a little bit of code that I prepared earlier to save a little bit of time. So let's just copy that. And we're going to call that from here. Right, so that is going to the C group directory, inside that going to PIDs, inside that going to a control group that I'm creating called Liz. And I'm going to write a file, I'm going to write a limit of 20. So I'm saying inside my control group, there can only be 20 processes. And the other important thing that I'm doing here is this last line here, where I'm getting the current process ID with that get PID, and I'm writing it into a file inside my control group called cgroup_procs. And that's adding my process, is saying this process is now a member of this control group and is subject to the same limits. Okay. Let's run that. So go run, bash. Okay. From my host, I should, well, I've got a Liz directory, and let's make sure we've got the maximum that we expect. Yeah, so should be limited to 20 processes inside this C group. And let's just check, again using that trick with sleep. I'm going to find the ID of that process, 8563. And if we look in that cgroup_procs file, 8563 automatically got added in there because it's a child process of whatever, presumably 8543, which was the kind of first of these containerized processes. So inside my container, I should only be able to create 20 processes and no more. So let's put that to the test with one of these. Who knows what that is? It is a fault bomb. Right. So how that works, we define a function called colon. And in that function we call colon, we pipe the results into colon, which we run in the background. That's the definition of our function, and then we invoke it. So it should keep calling itself, creating, just forking processes forever. But hopefully it will be limited by my control group. Just double check that I'm running it inside the container. Let's give it a go. Okay, so it's having a bit of a go at trying to fork a lot of processes, and it's clearly not able to fork as many processes as it would like. From the host perspective, well, for a start, I can type perfectly okay. Nothing bad seems to be happening in terms of the responsiveness of my host. And this is here's my go run main.go. Here are some defunct processes. We will never see more than 20 processes in there. We can look at PIDs current, which should tell us the current number of processes, and there should be 20 of them. We can look at, if we look at C groups, what we'll actually, cgroup_procs, we'll actually see the parent processes. We don't see the full threads, but if we look in tasks, we should see that probably, maybe we didn't get the dead ones, maybe we don't get the defunct ones. Anyway, we can tell from the PIDs current that there are no more than 20 being created. And yeah, we can continue to use the computer rather than it having been completely destroyed by that fault bomb. Don't run a fault bomb on a machine unless you know it's constrained by a C group. That's my advice to you. Okay, so we have seen how a container is created from namespaces and limited by control groups. We've seen how the file system works, or how images work by pointing you at a subset of the file system on the host. We've seen how to bring a machine down by using a fault bomb. Don't do that. If you want to check out the code, you'll find it in that literalized containers from scratch repo. I definitely encourage doing that and playing with that and building your own container if you want to really kind of understand how these things work. Now, those of you who had your hands up earlier that are running containers, do that again. If you're using containers, put your hand up. And leave your hand up if you are doing vulnerability scanning on your containers. Yeah, quite a few of you are not. It's a very good idea to scan your container images for known exploits. That microscanner is a free-to-use tool for scanning your images, so I just wanted to give a quick shout out to that. With that, I really hope that you now leave with a fuller confidence that you understand what containers are. Thank you very much. And I think we have time for a few questions, if there
Yes, please. Questions? Start first one. What do you think about Dockerizing database like Postgres?
What do I think about Dockerizing a database like Postgres? Why not? I think as you can see there, what you're doing when you run something in a container, it's still a Linux process. The thing that is different is where the storage is. So with anything that's got state, if you want that storage to persist, you have to make sure that the executable stuff is looking at a storage system that's persistent. If you were just talking about one host, you could just mount the Postgres or whatever into the container, and that would be exactly the same as running Postgres on the host, looking at a local file on disk. The difference is that when we start talking about containers, we're really talking about distributed systems. We're talking about that storage being somewhere else, probably in the cluster. And we're saying, I want to be able to create my container anywhere in that cluster, and I want it to point to that storage. And then, but mechanisms exist to do that. So, yeah, there's nothing wrong with running Postgres inside a container. It's the storage that matters for that.
Do you think it's a good idea to run Docker in Docker?
Do I think it's a good idea to run Docker in Docker? There are very few occasions where you really need to run Docker in Docker. There are. Struggling to remember what they are. Now, one of the reasons why you might not want to do it is that as soon as you do that, you're running with the privilege flag, which means it's not just root, it's root with full capabilities across the whole machine. Run Docker in Docker if you need to do something particular for your application. Don't run Docker in Docker just for the hell of it.
Any other questions?
Okay.
Oh, it does now. I think it just came on as you left.
So, thank you. It's actually great that nothing's been broken in your demo. It's actually, I think it's a very big achievement. A question, if you have tools, like some of them, like Java, before 10, or I don't know, the 3, if I'm not mistaken, which are not container aware, where they are getting the information about the memory or CPU, which is being granted to the container itself. So, for example, like a Java, you're doing like amount of memory, basically shows that the whole machine is being available for the process. Why it's originally not, just solved on the Unix level, just to restrict it to the process itself?
Yeah, I don't know enough about how Java works. I mean, I know there is the Java virtual machine. I'm not a Java person So I'm definitely moving into the world of speculation here. On your Linux kernel is using that mechanism for doing things like limiting memory. My assumption would be that the virtual machine, the Java virtual machine, would be grabbing a bunch of memory up front and then dividing that up in different ways that the kernel is no longer aware of, but I'm pretty much speculating at that point. Anybody, any Java experts want to tell us? Okay.
Should I still use VMs to run Docker on bare metal?
Should I still use VMs to run Docker on bare metal? Sort of depends on the application and sort of depends on what you're, you know, if you're running your own data center, you might use VMs for the ability to create and destroy VMs really quickly and to sort of repurpose your machines pretty quickly. You might run containers in VMs for isolation purposes. So we've just seen that containers are, you know, they're Linux processes. If I had 2 of those, they're still sharing the same kernel. All the containers within a virtual machine are sharing the same kernel. So there are, to say it's, if there were a kernel exploit that allows you to escape a container, well, you know, if there were a kernel exploit, it's a shared kernel, so there is potentially a risk that says if I can escape a container, I can see the other containers on that VM. It's much harder to escape a VM. So for like pretty specific security reasons, you might say, I want to run my containers in separate VMs. A really good application of that is if you're doing kind of multi-tenancy. So you have groups of people who, you know, you're running code on their behalf, but they don't trust each other. So putting each of them into their own VM makes them less, well, it makes it more secure for each of those tenants. Any more questions?
Okay. Thank you, Liz.
Thank you very much.